going to pick up on circuits for the fourth objective, which is analyzing complex circuits. I'm also going to include a link in the email that's going to go out to announce that this video has a link and all of that. I'm going to include another link to a set of practice problems that are on the website, the Physics Aviary, the one that I've sent out before to a couple people for extra to reassess on. Basically, it's a website that's going to have practice problems that will automatically regenerate with different numbers, and so you can try out different circuits, the same type of circuit just with different numbers. And so what I recommend is once you've gone through this packet, you've answered the questions, you've watched all the videos, and you still feel like you need more practice on any type of circuit, go to the link and complete the problem. Complete the types of circuits that are the ones that you feel the weakest on. There are also YouTube links on how to solve circuits like that included in the on that website. All right. So for this one, we're going to talk about for complex circuit analysis. We're going to talk about how you can approach a problem where you see parts of the circuit are in series, parts of the circuit are in parallel. There's another resistor here that's in series with this whole system, and like there's a lot going on, right? And so there are a couple big key points that we're going to talk about throughout the whole process, and those 3 points are the following. As you read through here, you'll stumble upon the strategy. And so our strategy is going to be to do these 3 things. We're going to first simplify the resistor network until all the resistances are combined into one equivalent resistor to find the total resistance. What does that mean? That means you see 2 resistors here, 2 resistors here. You know that these 2 resistors are in series, and these 2 resistors are in series as well. So what you can do actually is just do something where we replace them. Let's say, okay, so there's R4 and R5. That's going to be call them one big resistor. So we add the resistances here, R4 and R5, and over here we replace this segment of the circuit with another resistor. But this resistor is R2 plus R3. So we just add those 2 resistors in series, and then we have one resistor and another resistor in parallel. Then what we can do is actually combine these 2 resistors in parallel. So then we get one big single resistor that's right over here. And this single resistor is 1 over Req, because this is how we add resistors in parallel, where you have 1 over R2 plus R3 plus 1 over R4 plus R5. Basically, we have 2 combined resistors in parallel. And so that's one big resistor. And then you have this resistor and this resistor are now in series. And so you just replace this whole thing with one resistor. And that's the total resistor. Oh, whoops. That is one way of figuring out what the total resistance is.
The 2 different examples that are included in the problems. Okay. So we're going to simplify the resistor network until all resistances are combined into one equivalent resistor to find the total resistance. Got that. We're then going to use V is equal to IR to find the total current. Once we found the equivalent resistance, which is that, once we always go and know the total voltage, we'll be able to find I to find the total current. Now, once we find the total current, then it's like a little puzzle. We're going to work backwards and figure out, based off of the total current, using the equations for series and parallel circuits, what can we figure out about each part of the circuit? So, these are our 3 steps in the process. I'm going to keep these up here. We're going to continue to refer to these as we solve the problems. Let's get started. So read through this if you want like a step-by-step breakdown, if what I'm going over in the video doesn't quite gel. And also watch these 2 videos right over here. These 2 videos are really awesome, like really, really awesome. Especially this guy right over here, Doc Physics. Doc Physics is the name of the channel. He does a really good job with explaining things, and
This dude is like super excited. It's pretty great. Okay, so the first 3 questions are really warm-ups to getting into the process of analyzing circuits. I'm not asking you to figure out anything about the components of the circuits just yet. All I'm doing is asking you to find the equivalent resistance between 2 points for 1, 2, and 3. Now, I would say 1 is pretty mild, 2 is spicy, and then 3 is V-spicy. I actually didn't have a chance to, or I forgot to label these by difficulty earlier. So I'll draw. Fire emoji right there. V-spicy. Okay. Oh, before I forget. So I went to Puerto Rico. In Puerto Rico, I won a certificate of honor. And the certificate of honor is because I tasted the Caribbean Trading's Insane Crushed Pepper Sauce, and yeah, I had the spiciest sauce at this place in Puerto Rico, and they gave me a cool certificate. Yeah, I would say this is fairly accurate, the part about extraordinary courage and definitely rather dubious judgment. I would highly not advise you to do spicy food challenges. It really just, nobody really wins. Like, I got this, but I don't really feel like I won anything. I'll tell you more about it when I see you guys on Monday. All right. So, equivalent resistance between points A and B. So as we look at this circuit, we can see that from point A to point B, immediately we know that the current is going to go in 2 different directions, right? So the current can either go here or it can go here. So immediately we have 2 branches, right? From point A to point B, I can either go foom, 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 or I can go do, 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 do. Now, that means if there's a junction here, then this is one branch, branch number 1, and this is another branch, branch number 2. Now, in branch 1, there's only one resistor. So this branch has a resistance of 1 kilo ohm. Now, this branch, however, on the other hand, has a resistance of 3 kilo ohms because you have R1, R2, and R3. They're all in series. We have to add these resistors to get the total resistance of this branch. So let's combine these 3 to form, let's redraw this circuit so that it's only one resistor. So this is A and this is B. This is still 1 kilo ohm, but now this is all 3 of these resistors combined, which is 3 kilo ohms. Because all we have to do is add these 3 kilo ohms, right? So RQ is equal to R1 plus R2 plus R3 when in series, right? Now, we have one resistor and another resistor, 2 different branches, so these are in parallel. So we need to actually add these in parallel. So that's 1 over REQ is equal to 1 over 1,000 ohms plus 1 over 3,000 ohms. This is because these 2 are in parallel. This is how we find the equivalent resistance. I'm going to make this 3 over 3,000 plus 1 over 3,000. And then this is going to be 4 over 3,000, 1 over REQ. So now if I'm solving for REQ, I know that REQ is just going to be 3,000 divided by 4. When we divide 3,000 by 4, we end up with 750 ohms. And so we've found the equivalent resistance of this circuit from A to B by first adding these 3 resistors in series and forming one big resistor, and then combining that big resistor of 3 kilo ohms with the other resistor on the other branch, and that was in the circuit. And then when we added those 2, we did it in parallel, and we ended up with 750 ohms. Cool. Now let's do the same thing, but for number 2. All right, let's take a look. From point A, we have some current that travels to the right and some current that travels to the left. Now, as the current goes down here, okay, so it's going to go encounter this resistor and then stop here at this junction and then go there or go there. Okay, so as it goes from here, and then it'll come back to B. If the current goes onto this side, it's going to go through the 2 kilo ohm resistor and then go to this point and then can go either there or there. So here's one thing that we know. Because there is a junction here and here, the current that's going into this segment of the circuit can then go into this segment of the circuit, right? So these two resistors are in series, right? Same with these two resistors. These are in series as well. Now, this resistor is also in series with this resistor and that resistor, because you can have current that goes through here and then goes down over here and over here. Current will never go backwards, but current has to pick between the left and right branch initially. So what we know is that these two are in parallel, these two are in parallel, right, because there's two separate branches, but the whole thing, the top and bottom, are in series. And so we can approach this by first figuring out what the equivalent resistance is for these two resistors in parallel, and these two resistors in parallel, so we have to redraw the circuit. So let's do that right over here. Oh, oops. And this is just the equivalent resistance of these two. So I'm going to call this R1, and this R2. And so then R1 is equal to, 1 over R1 is equal to 1 over 2 kilo ohms plus 1 over 5 kilo ohms. If we do some math here, we can see that we got 5 plus 2 over 10 kilo ohms, right? This is some old school mixed number or fraction, I don't remember. So then R1 is equal to 10 kilo ohms over 7, which is equal to, I think, 1 point something. Let me check my calculator. So 10 divided by 7 is 1.4. Yeah. So R1 is equal to 1.4 kilo ohms. That's the sum of these two. Now we have to sum these two. And so these two are also in series. Let's say 1 over R2 is equal to 1 over 100 ohms plus 1 over 470 ohms. Then we have, it's a little bit more complicated, but to get from 100 to 470, we can just multiply this bottom number by 4.7. So when we do that, I'm going to bring it a little bit closer. Cool. When we do that, we get 4.7 over 470 ohms plus 1 over 470 ohms gives us 5.7 over 470 ohms. Now 1 over R2 is equal to 5.7 over 470. Therefore R2 is equal to 470 ohms over 5.7. So what that means is that we've found R2 right over here. Easy money. Let's see, 470 divided by 5.7 gives us around 82.5 ohms. So R2 is equal to 82.5 ohms. All right, well, let's take a look. We got R1 and R2, and now from A to B, the equivalent resistance is just going to be the sum of these two because it's in series. So the total, I'm going to write this over here, REQ is just going to be equal to R1 plus R2. If R1 is 1.4 kilo ohms, and R2 is 82.5 ohms, the total equivalent resistance only is going to be around, what, 1.511 kilo ohms, right? 1.4 thousand ohms plus 82.5. So you got that number right over there. Cool. Now, this problem is V-spicy, like V-spicy. And so what I'm going to do is I'll walk you through it real slow. All right, so now,
in this example, let's get up close and personal with this page. In this example, we see that if the current is going to the right, it's going to encounter this 100 ohm resistor. All right, that's cool, fine. Current's going that way. Boom, it gets hit back by that 100 ohm resistor. Now it's at a junction. So it's flowing through and now it's at a junction. Now, this junction has an option. It can either go into this branch of the circuit or it can go to point B. Now, if you're current and you're thinking about taking the path of least resistance from one side to another, you're probably not going to go back into another resistor, right? At this point, you can get to the other side of the circuit. You can get to where you need to go without going through another resistor. And so what you're actually going to see is the current that goes into this branch go more often than not from this junction straight to B, because the current is going to want to travel to the path where it has the least potential and encounters the least resistance in doing so. That means that this branch is effectively just the 100 ohm resistor. Now, what does that mean for the current that goes into this branch? Well, that means the current that's going to go into this branch is going to split. So from here you have some current that travels into the 220 ohm resistor, but that current can then either go into 470 or 330. So in the end, what you really have is something that looks more like this. And one of the best ways to really understand circuit problems is to try and redraw the circuit so that it makes more sense. One of the things that happens when we see problems like this is that we get overwhelmed because they just look weird, right? And so part of us has to think about, okay, so this is pretty much going to be the only path for that from A to B. We have to make our own diagrams. It's totally fine. And so then one over here, and then these are going to rejoin and go back to B. Or sorry, they're going to be separate paths to B. So this is the 220 ohm resistor, and then the current's going to split up into two, and then you have a 330 on one side, and you have a 470 on another side. Right? We see that? And so this is basically the same thing as this circuit. I just redrew it, so it's a little bit easier to process. So now it's easy as toast because we have two circuits in series. So our first step would be to, or in parallel, our first step would be to find REQ here. So combine these two. And then we can see that once we find REQ here, we can combine here to find, we'll find REQ again, but now it's the sum of this resistor and then these two resistors from step one. And then the final step is just combining all of it, right? Because you have this combined resistor for step two, and then you have from step two, and then you have this 100 ohm resistor on this side. So step three is actually putting the whole circuit together. Let's do it. So the first step is REQ between 330 and 470. So 1 over REQ is equal to 1 over 330 plus 1 over 470 ohms. And so these are a little bit trickier because these are kind of gross numbers. Probably the easiest way to do it is to just multiply these two together instead of trying to find a least common multiple. Just multiply them together. So then you'll have 470 over 470 times 330, whatever that gross number is. 330 times 470. Yeah, so over 155,100 ohms plus 330 over 155,100 ohms is equal to these two added together. So 470 plus 330 over 155,100 ohms. That's 1 over REQ. So REQ is then going to be equal to 155,100 divided by 800. So RQ will be just the 193 or 194. This is probably the most annoying part about circuits, is just adding things when resistors are in parallel. So that's REQ for this part. Now that's one circuit. So now we've done this. We've gone from here to this circuit.
Still got that 220 ohm resistor lying around, but we have now a combined resistor that goes to B.
But now we have 220 and then 194 ohms. So now what we have to do is combine these two together in series. And that's easy because we know that when you're finding resistors in series, we just add them. So we got 220 ohms plus 194 ohms is equal to 414 ohms. All right, so now we have finally like a pretty easy circuit. It took us some time, but we got there. We got 414 ohms here, and we have the same 100 ohms from before. So now we have a circuit that's in parallel with two resistors. Light work. So to find the equivalent resistance here, we do the same thing we did in step 1. Really, the thing is just having enough paper and space to do this. Yeah, I highly recommend doing these on another piece of paper. I wanted to just keep it on one paper for you guys to do on these, but you do definitely need more paper. 1 over REQ is 1 over 114 ohms, or 414 ohms plus 1 over 100 ohms. Now, for this one, we can just do 1 over 414 ohms plus 4.14 over 414 ohms. So we get 5.14 over 414 ohms. That's 1 over REQ. So then REQ is just equal to 414 ohms divided by 5.14. When you divide those two numbers together, you should get something close to 80.5 ohms, which is in fact the answer that we have here. All right, and now on to the tougher problems, and we want to use a table to always organize our work. So what I'm going to do is actually I'm going to draw on another circuit and then, draw on a separate circuit right over here, just so that we can see the steps of what's happening before we fill out the table. Okay, so this is a circuit that we're starting with, right? And on this piece of paper, I'm going to draw how the circuit develops over time as we work to simplify the resistor network. And then from there, after we simplify the resistor network, then we're going to find the total current, and then we're going to do the math and put it in here. Okay? So, but like first, we need to find what the double, or we need to figure out what the double is going on with all these resistors. All right. So right off the bat, here are things that we want to identify. We know the current's going to travel out from this 12-volt battery. We know the current's going to go this way, and it's going to encounter this resistor. All right, so after it encounters this resistor, it's going to split at this junction to form, to go into this branch and then this branch. Now, from that point, current that went into this branch is going to go back in here, right? So that's one resistor and one resistor. That's one full circuit right there. The current that jumps out from this loop, jumps out into this loop, is going to go into this resistor. But then after it goes into this resistor, it's going to go to this junction. It's probably not going to go back to R2. Like, it's definitely not going to go back to R2. So you actually have one complete circuit with R3 and R2 in series, and then one complete circuit with R3 and R1 in series. And so we actually know that these two are going to be in parallel. So we find the sum of those, find the equivalent resistance there, and then find the equivalent resistance of R3 and both of them combined with by adding them in series. So the next circuit that I'm going to draw is going to look something like this. R3, then one over R2 plus 1 over R1, right? Because we added these in parallel. Then we got this. Because we're adding these two in parallel, or in series, we then will end up with a circuit that looks kind of like this. 12 volts, and then R3 plus 1 over R2 plus 1 over R1. Because that's what this little bad boy is. Alright, so now let's do some math and justify. Actually, we can just plug in the numbers here.
Yeah, I mean, I'm going to do this one first, and then I'm going to plug it in here. All right, so R2 is going to be 130, so 1 over 130 ohms plus this is actually incorrect. So this seems to state that the equivalent resistance is 1 over R2 plus 1 over R1. It's not. It's the reciprocal of that. See, because this is 1 over REQ is equal to 1 over 130 plus 1 over whatever R1 is, which is 220. Okay, so now we're going to add these two. Once again, I'm going to take the really lazy route of just brute forcing it, finding the least common multiple by just, or finding some multiple, not the least common multiple, by multiplying this by 220 and then multiplying that by 130. So we end up with 220 ohms plus 130 ohms divided by whatever the product of those two numbers is. Shit, 28,600 ohms. Cool. Now, plus 130 is 3, can I do basic math? Yeah. Boom, look at that, 350 ohms over 28,600 ohms, 1 over REQ. Now, REQ is just going to be the inverse, right? So 28,600 ohms divided by 350 ohms is going to be equal to 82. 82 ohms. Cool. So the 82 ohms is going to sit here now. That's 82 ohms. Now R3 is still 470 ohms. And so we have 470 and 82 when we have 470 over here plus 82 ohms. So the total circuit, the total resistance in the circuit is just the sum of these two, because if they're in series, we can merely add them. So we end up with 552 ohms of resistance in the circuit overall. Okay, so now let's go back. This was step 1 of the process, find the equivalent resistance in the circuit. Now, let's go back over here and put in the equivalent resistance of 552 ohms. Now, we have to use that little blurb to find the total current, because we know that V is equal to IR. If we're solving for I, we know that I is equal to V over R. So you have 12 volts divided by 552 ohms. That should give you 0.02 amps. Alright. Now, this is where things get a little funky, because now that we know that there's 0.02 amps flowing in total throughout the circuit, what we can do is say, okay, from here, there's got to be 0.02 amps going into R3, because that's the first thing the circuit encounters. And then from here, it's going to split up, and then we don't know what the current is here or here. But what we do know is that the voltage drop across these two resistors has to be the same, or across these two branches has to be the same. So the way what we want to do first is figure out, okay, if we have the current going into R3 and we have the voltage going into the resistance for R3, we can easily find the voltage for R3, because we also have V is equal to IR. So V, in this case, V3 is equal to I times R3. And so the voltage is going to be equal to I, which is 0.02 amps, times the resistance for number 3, 470 ohms. So the voltage drop across this resistor is going to be 0.02 times 470, 9.4. All right. Boom. So this, right, so the current is actually the same for total as it is for R3, 9.4 volts. This is helpful because we know that 9.4 volts have already been dropped off, so the remaining volts left over have to be split up by these two resistors. But we also know that the voltage isn't going to split. The voltage is not going to split. The current is going to split. So we know the voltage drop across both of these resistors is the same, and it's whatever's left over. So that's 2.6 volts and 2.6 volts. That's 2.6 plus 9.4 is 12. And so R1 and R2 are each getting 2.6 volts, but they're not getting the equivalent amount of current. We know that because they each have different resistances. So we know that because this has a higher resistance, this is going to encounter less current. Because this has a lower resistance, it's going to encounter more current, right? Same voltage. Here, so for 2, we want to find the currents here. I is equal to V over R. Higher resistance, less current. So let's do this. For I1, we know the voltage is 2.6 volts over whatever the resistance is here, which is 220 ohms. I'm going to plug it all in my calculator at once. I2 is equal to 2.6 volts divided by 130 ohms. So 2.6 divided by 220 is equal to 0.012. On the flip side, we have 2.6 divided by 130 gives you 0.02 amps. Sick. So now we have all of the currents, all of the voltages, so power is light work at this point, because P is equal to V times I. All we have to do is just multiply voltage times current to get power. And so if we do this calculation for all these rows, we'll see that. 0.052 watts. 9.4 times 0.02, 0.188 watts, and then 12 volts times 0. So 0.24 watts in total. Now, this is not purely the sum of all of these. What it is actually the total current times the total voltage. So that's the total power dissipated in the resistor. Because some of the current is also going to go to, the current is going to split between R2 and R1, but they're not weighted equally, so we can't simply just add them. We have to be able to take the total voltage and total current and then figure out the power from there that way. Okay, now we found the total power in this guy. Let's do VV spicy and call it a day. All right, so I'm going to approach VV spicy in the same way that I approached the previous problem, V spicy. We have to go back and we have to simplify the resistor network, then we have to find the total current and then complete each section of the circuit with 2 rules from the previous section. So like adding resistors in series and parallel. Alright. Now let's take a look, see at this guy right over here. So you got a battery with 6 volts and you have one resistor and another resistor. Oh my gosh, I'm already overwhelmed. Deep breaths. Okay. Let's take a look. You just appreciate how much progress we've made. Like now we're looking at these guys. Before we were looking at like just one battery in a circuit and one resistor, and then soon we're going to be able to process these guys. Anyway, let's go back. So the current is going to come out of this battery, and it's going to go into this junction. All right. So as soon as it goes into this junction, it's going to split. So you're going to have some current going this way and some current going that way. Now the current that's going in this direction is going to encounter this resistor right over here and then rejoin the main loop at this junction. Then after it goes and rejoins this the main loop at the junction, it's going to have to encounter R2 and R1. So it's going to always encounter R1 and R2 and R1 in series. Now, for the current on this side, it's going to go, that comes out of the junction on this side. It's going to go all the way around, and then encounter this resistor, and then enter the junction, and then encounter R2 and R1. So, what do we got? We got parallel, we got series. So, let's redraw this the way that we really want it to look. So, the first thing we're going to do is add these two in parallel. So, we want one resistor first off, that is just this R1, R2, we haven't touched those yet, but we want one that's 1 over R3 plus 1 over R4, yeah, R4. Equal 1 over R cubed. So we have to do that first. And then once we've gotten that, then we're just adding this whole thing in series. So this one actually isn't too spicy. Let's get it. Let's find out what this equivalent resistance is first. So 1 over Req is going to be equal to 1 over R3, which is 470 ohms, plus 1 over R4, which is 6,800 ohms. I just rewrote it in ohms so that, once again, for consistency. Now, wow, that's a lot of ohms. So we'll say 6,800 ohms plus 470 ohms, all over whatever these two are multiplied together. It's going to be big. Let's see what it is. 470 times 6,800. Wow, so that's 3,196,00. Wow. That's a lot of resistance. So over here we have 1 over Req is equal to 6,800 plus 470. So on the top we got 7,270 ohms, and on the bottom we have 3,196,000 ohms, and so Req is just going to be equal to the reciprocal. Which is going to be equal to 3,196,000 divided by 7,270. So we have 440 ohms. Cool. So the first equivalent resistance is 440 ohms. Now the nice thing is that if this is 440 ohms and we know that R2 is 2,200 ohms and then R1 is 1,000 ohms, because these three are in series, this is pretty easy because we just need to add these three. So the total resistance is actually going to be equal to, we did the hard part, the parallel part, now we just add them. So 1,000 plus 2,200 plus 440, which is 3,200 plus 440, 3,200, 440, which is 3,640 ohms. So that's the total resistance in the whole circuit. Alright, let's put this guy in the table. Okay. We got excuse me, I'm sorry. We have a total resistance of 3.64 kilo ohms. Now the current is going to be back to V equals IR. So the total current is going to be, no, I'll do it up here. V is equal to IR. I is equal to V over R. The total voltage is 6 volts. The total resistance is 3,640 ohms. And so then we got ourselves a current of 6 divided by 3640. Pretty small. So 0.0016 amps. Yeah, with great resistance comes very little current. Now, we figured out the total current here, and so once we figured out the total current, we have to do a little bit of thinking to figure out how that current splits apart. So we know that if we look back at our circuit, the current has to go from all of the current, so all of this current 0.0016 amps must be encountered by R2 and R1. Like, that is in the main junction. Like, yeah, the current's going to split up here and here, so for R3 and R4, we don't know how much current each of those is getting, but what we do know is that R2 and R1 are going to get all of the current, right, because that's in series with the battery. It's in the main loop. And so for each of these, R1 and R2, we know that the current is going to be 0.0016 amps. So that's an immediate tie into the voltage. And now, one thing that we know is that if we can find the voltage that R1 and R2, the voltage drop across R1 and R2, we know what the voltage drop has to be across both R3 and R4, because the remaining voltage that isn't taken up by R1 and R2 has to be the voltage drop across both of the resistors, R3 and R4, because they're in parallel. So let's figure out the voltages for R1 and R2. So V1 is equal to I times R1. So we got 0.016 amps times the resistance, 1,000 ohms. The resistance, V2, I times R2 is equal to 0.0016 amps times 2,200 ohms. So we multiply these two together. Wait, do I really need? No, I don't need a calculator for the first one. So 1, 2, 3. So 1.6 amps or volts. Whoops. On the flip side, we got 0.0016 times 2,200. It's got 3.52 volts. So we got 1.6, 3.52. Now we know that the remaining voltage, so 1.6 plus 3.52 is 5.112. So the sum of these is 5.12. 6 minus 5.12. So 0.88, that's the remaining voltage. It has to be the same for R3 and R4. So whatever isn't taken up by these two resistors, and it doesn't matter whether or not the current flows, yeah, of course the current's going to flow into this branch first, but the thing is, like, R1 and R2 are also taking away voltage, just because the fact that is that they take away the voltage from the current after they encounter R3 and R4, but that doesn't mean when we look at it to analyze the problem, we can't look at those first. Like, that's another thing that some students say. They're like, oh wait, we need to look at the very first component that the circuit, or that the current encounters, to analyze the circuit properly. No, it's not how it works. We can attack the circuit at any point where we see fit. So now moving backwards, when we have the voltage and the resistance for R3 and R4, we can figure out what the current is. So next step is I is equal to V divided by R. And once again, we're going to branch. So the voltage, so for I3, we have a voltage 0.88 volts over the resistance 470 ohms. For I4, we have the voltage 0.88 divided by 6,800 ohms. So I3 and I4 coming right up. We got 0.88 divided by 470. Oh, that's pretty small. I3 is 0.0019 amps, and then I4 is 0.88 divided by 6,800. Hey, we have a, whoa, that's a weird number. 0.0001. It's so super small. Why is it super small there? Because the resistance is huge. Of course, there's not going to be a lot of current going through that resistor. You have a really small, or you have a really high resistance. Why the devil would the current want to break off into this loop and then go through that resistor, that behemoth of a resistor, 6.8 kilo ohms, when it could just go through this pleasant little 470 ohm resistor on its way to the main branch? Like, come on, we want less resistance. There's obviously going to be more current going through R3, which there's a lot more of, by a factor of 10. So now that we've found the current for all the resistors, and because we know the voltage, like, come on, child's play. So we can find totals for power by just doing the casual P is equal to V times I. So 1.6 times 0.00 256 watts, 0.00256 watts there. And then we got 3.52 times 0.0016, 0.0056 watts, 0.88 times 0.0019 gives us 0.001672 watts. Oh, so much multiplication. This is probably the most tedious part of circuits. Or it is the most tedious part of circuits. 0.00, oh my gosh, 0088 watts. Super small. And then the total power, 6 times 0.0016 gives you 0.0096 watts. Alright? So I hope you enjoyed this video, and I hope that we had a good rundown of how to do all the circuit problems. This was pretty comprehensive. It's a long video. Let me know if you have any questions or concerns about any of this stuff. And I will share the link to the practice problems for all these types of circuits in the email. Alright, so stay tuned. Enjoy the rest of your break.